started the recording. So you can hear me, right? Both of you can hear me, right? Ayush, you can hear me, right?
Yes, sir. Yes, sir.
Okay, cool. Okay. So yeah, so sorry for yesterday's mess up. So today I ensured I kind of there was a laptop issue yesterday. It was not a laptop issue. Most likely it was a Teams issue. But anyway, so today I ensured that things are in place. So let's proceed and we'll try to make up for lost ground. So anemometer, as we started the discussion yesterday, so this is one area that you will see in the subsequent slides, right? Where I found the textbook mentally to actually not do a decent job of it. I mean, they have done a mathematical approach. They have taken a mathematical approach, but somewhere I'm not convinced with that approach. Even though the final answers are, the final equations that they have derived, the book has derived. I don't have a problem with that, but the way it is done and the maths behind the sensors, I didn't agree to that. So I will try to, in the next few slides, I will try to explain the sensor and the maths behind it in my own way. And if you were to refer Bentley, you can refer Bentley also. You can see how my approach is different from Bentley's approach. And probably, hopefully you'll appreciate why I have taken a different approach to arrive at the same solution. The final answer is correct, and that is actually one of the key things. Even assignment 1 that I had given, or question number 2 in mid-semester exams, right? I mean, and even in the class I had mentioned that, look, it is not about somehow getting a relation between the variables, right? The way we apply the equations and then arrive at the equation, arrive at the relation, that is important to me. It is not that, I'm not giving you to, just do an algebraic replacement and then come up with an answer. That anybody can do. For that, you don't have to be in IIT and studying engineering, right? So, so the same thing holds here also. In the next few slides, you will see what is important is if you are not convinced with the approach, right? You are free to, explore your own, methodology to kind of find the solution. Even the last problem, I'll probably take a class where I will discuss some of those problems that I had thought and I had given. The last problem of mid-semester was actually a solution to assignment 2 that I had given. I don't know how many of you guys have realized that the assignment 2, I had asked you guys to come up with an expression or a circuit which takes care of the low frequency issue. And if you look at problem 5 that I had given in mid-semester, that actually took care of the issue. I don't know how many of you guys have realized that. But anyway, so in the next few slides, you will see the anemometer approach that I have taken is again quite different from the way Bentley, the book, has taken. And hopefully you will agree with me. So let's start. So yesterday we discussed, we saw the structure of the sensor, and we also discussed why the wire needs to be normal to the velocity. And in fact, I will show you some pictures of state-of-the-art sensors, like sensors which are being sold in the market and which has been designed as late as 2020 or 2021, and how they look like. I'll show that to you later. But for deriving the equations or understanding the relation, it is important to understand why we are assuming the velocity of the fluid to be normal to the wire, right? And looking at those equations yesterday, what we saw is at steady state condition, I square RW, the heat that is generated inside, or rather the heat generated because of the current flow in the tungsten wire, right? That will be equal in the steady state condition. Please remember this is valid only in steady state condition, right? So the heat generated in the wire will be equal to the heat that is dissipated by the wire, right? Because of the fluid flow. If the fluid is not flowing then of course, the dissipation will be something, and if the fluid is flowing faster, right? And if there is a temperature difference between the wire temperature and the fluid, then, I mean, it's very common sense, right? We can understand even without looking at the equation that this is going to happen. If the fluid is flowing faster, then more amount of heat is going to be removed by the fluid that is flowing, because of which the steady state temperature, TW, will be settling to something else. And yesterday we saw that what are the variables that we have in this equation. RW is actually a dependent variable, right? Because why RW is a dependent variable? Because it's the resistance of the wire, which is a function of the temperature. And that temperature is denoted as TW. So TW is itself a variable, and RW is a dependent variable depending on the temperature of the wire. J is again nothing but a constant, right? A mechanical equivalent of heat. Area we know. So these two constants, A and B, these are also like constants, which again we are not deriving it for now. And this is the temperature of the fluid. So we can show that at steady state, the equation of the heat generated in the sensor wire and the heat that is being taken away by the flowing fluid will have this kind of a relation, wherein, if the velocity is higher, right, if the velocity is increases, right, to achieve the same temperature, we would need a higher current. It kind of makes sense, right? If the velocity flow is increasing, then if the temperature TW, if we want the temperature of the wire to settle to a certain fixed value, then for the same, for a higher value of velocity V, fluid velocity, the current that needs to be flown in the wire has to be higher, right? It kind of makes sense. And then we saw that, look, we said that, we have two variables in the equation, which is current and the other one is temperature. And this is actually the fundamental principle behind two types of sensors that we are going to design. That's what we're going to study, right? So the first one is where the current is under my control. And what I mean by control is I can change that if I want. And I will treat that current to be, let's say, a constant. I will ensure that the current that is flowing through the sensor wire is fixed, irrespective of whatever the resistance of the wire is or the temperature of the steady state temperature of the wire that becomes, right? So I can make this guy fixed and let TW and RW vary, right? Or the second approach can be, I can vary I square, the current that is flowing through the sensor, and ensure that the temperature of the wire is maintained at a constant value, right, or a level, right? So we can take two approaches. So with that, let's look at the first one. And please understand, we are discussing these sensors. Why are we discussing these sensors? Of course, to understand how they work, but we are also going to establish the importance of feedback in a system, which is what I started the lecture with yesterday, right? I took a very simple electrical example and explained, I drove home the fact why feedback is important and what are the benefits. And of course, as with everything else in life, benefits don't come alone. If you have to get some benefit, you have to pay some price also, right? So we said that, look, there will be a price in terms of design complexity, power, cost, and all that. But having said that, we did establish that proper feedback mechanism does bring in added benefits of improved bandwidth, improved drivability, right? And blah, 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 right? We can talk about others. So we are discussing these sensors in that context. So it's important to understand the context of the discussion. See, I am discussing a sensor. Why am I discussing the sensor? Not to show you some equations, right? Of course, we will look at the equations, but the goal is to understand the basic principle of feedback. Okay, so let's look at constant current anemometer. So with that context in mind, let's approach these two sensors, these two kind of constant current or constant temperature anemometers, right? So again, what we are writing, so this is a dynamic equation that we are writing. Why am I calling it a dynamic equation? because we are not saying that the sensor has achieved a steady state value of the temperature, because so if you see here, what I have done is in green, I have kept the variables which are not fixed. It's not constant. Please note, I have marked it as black because this is a constant, and it comes from the very fact that we are designing a constant current anemometer, right? So the fact that we are keeping the current constant, RW is supposed to vary. UV is nothing but it is the convective heat transfer coefficient between the sensor and the fluid. It depends on few things like the sensor wire mass and the sensor wire specific heat capacity, right? So for us, the important thing to remember, of course, we have to care about the dimensions and all that, but we will say that, for us, what is important to realize is UV is proportional to the velocity of the fluid flowing across the sensor, and that kind of makes sense. What probably is not very intuitive is why the square root comes from. So that I think we'll leave it to our physics friend, and we trust them that they have done a good job and derived this equation properly. But we do understand that it is going to be proportional to the velocity, right? Just the one thing to remember, that probability is proportional to the square root of the velocity. So with UV multiplied by A and the temperature difference, TW minus TF. So TW keeps on changing, right? As the fluid velocity changes, TW is changing. We are letting it change. And that equals, so basically if you see, this is the heat that is generated in the wire. This portion of the heat is actually what? This portion of the heat is what? This is being dissipated in the fluid, right? Because the fluid is flowing, we are losing some amount of the heat energy in the fluid. So this portion of the equation tells us that part of the story, right? And whatever is the balance, meaning whatever is the delta between the heat that we are gaining and the heat that we are losing, of course, is going to result in what? It is going to result in increase of the wire temperature. And that is what we are writing as dTW dt as a function of time. Please understand this, dTW dt, because we are dealing with, here we are dealing with power, right? We are not dealing with, we don't have time. If you really look at it, we are not talking in terms of energy. We are dealing with the power or the, the heat that is being generated in the overall system is because of the power, the electrical power that is generated in the resistor minus the power that we are losing in the fluid, that whatever is the delta between that results in increasing the temperature of the sensor wire. And how much temperature will increase? Of course, it depends on the mass, right? And so basically, if you see, the wire is going to heat up more and more if the mass is what? Higher or lower? Think just from a normal thing, right? For this, if the delta energy remains same, what will be the delta temperature? If the mass increases, what will happen? What will be delta dt? What will happen to this portion? It will reduce, right? Because mass comes. If you see, if this portion is constant, dTW dt is inversely proportional to the mass, right? It kind of makes sense. The larger or the bigger the sensor material, the lesser will be the overall temperature increase because of the same delta in the power that is being generated and the power that is being dissipated, right? And of course, C is the sensor wire specific heat capacity. This is dependent on the material of the wire. And mass also, we are not going to change. The mass remains constant, right? That is also not going to change. Okay. And in equilibrium, of course, we know, which is what we saw in the last slide also, that we can equate that in equilibrium, what will happen? That there is no increase in temperature. The temperature will, so we will assume that the velocity is not changing with time. The velocity is constant, and the fluid, actually this should be black. I'm sorry for this. This should be black. So the fluid temperature doesn't also change with time. It's a fixed quantity. What changes is the resistance and the temperature of the wire based on the temperature fluid and based on all these factors, right? And in equilibrium, at equilibrium, the temperature of the wire is not going to increase. Fair enough, right? Not a big deal. Okay. So now let's see. Now that we have the equation at equilibrium, let's see what happens if we move the variables around the equilibrium point, or in other words, we can also say this is the operating point, right? I mean, operating point and equilibrium point, essentially they are not the same thing, but here I'm going to use them interchangeably because we are trying to derive a small signal equivalent. In the electrical block diagram that I showed you, I did discuss why the operating point is important, right? So around this operating point or equilibrium point, if we assume that the current that is flowing, that changes by delta I, right? I changes by I0 plus delta I. What will happen if the current changes? If delta I is positive, the resistance also will increase, right? Why will the resistance increase? Because if you see here, if the current is changing, if we increase the current, the amount of heat that is going to be generated in the wire is going to increase. So the overall heat that is left for the sensor material to increase its temperature will be more. So delta TW dt will be positive, right? So essentially with increasing current, it is obvious, or it is kind of understandable, that the resistor also will increase. So let's say the resistor changes, the resistor value changes from the equilibrium value of the resistor, RW0, it changes by a delta amount, okay? And also, because the current we have increased by delta I, the temperature also, as I said, will increase from TW to TW0 plus delta TW, right? And the other thing that we need to understand is UV0, right? Which was nothing but this convective heat transfer coefficient. This also is not, it's not like a constant thing. This is also a function of the fluid velocity. So what we will say is, without actually drawing the graph, how UVW, so maybe UVW will be, so if we draw UVW as a function of velocity, right? What do we expect? What sort of a curve can we expect? Any comments? How will UVW look like with respect to velocity? Any comments, guys? Give me some answer.
Like inversely exponential type, like.
Do you think it will be exponential? Okay, like this, or do you think it is like this?
No. First one.
First one, right? Yes, right. So I think what you guys are saying, it will be like this, right?
Yes, sir.
Right. Because we are talking of the heat that is going to be taken away by the system, right? Okay, one thing I like to clarify here, guys. I think the general feeling that you guys might have that this is a theory that is there in the textbook, old textbook. So it may not have much relevance in the modern world, but trust me, that is not the case. And I will show you, we will discuss, sensors which are being designed, the state of the art. So please understand, whatever we are designing, just because your textbook looks old, that doesn't mean that these sensors are not going to be used, or you are not going to come across. Of course, if you choose to go into a career of electronics or a systems engineer, you will come across such sensors. So please, have trust in me that even though the textbooks might be old, but the basic concepts, of course, the state of the art will be much more evolved, right? It will be having, I'll show you some of the software, or, I'll show you some of the equipment. I have some snapshots of the equipments, but please understand that this is very much relevant in the modern context. Okay. So now with UV and UV, so this, let's say we are just saying that, okay, whatever be the graph, we are not interested in the graph. but we will say that, because we are talking of an operating point, UV also will be changing based on UVW plus sigma times delta V. This sigma is nothing but the slope, and this kind of makes sense, right? We have a slope at this point, and we can assume it to be an incrementally, we can the delta V, we can assume it is changing incrementally, and the incremental change in UV will be nothing but the slope, right? So the slope multiplied by delta V, if V, this is V, right? This is what is going to be a new UV, right? And this is a fair enough approximation to make around an operating point, provided this delta I or delta RW or delta TW is much smaller compared to I0, RW0 and TW0, right? Okay. So with that assumption, so now that we have set the context, so let's punch in these variables, right, in this equation. Or rather, I should say this equation, I should say we should put those variables in this equation, right? Because this equation is a steady state condition, right? We should not look at that. So with that, now if I replace I with, whatever, I have just replaced this, right? So nothing, you can just look at it. I mean, I don't have to explain this portion. It is just a variable replacement. So once that is done, and I do some basic simple math, and of course some approximation. Engineering is all about approximation. Science is not, right? Because we as engineers, we have to make approximations. Otherwise, we will not be able to proceed. Meaning, we will not be able to talk to each other, right? Engineering is all about understanding the equations and doing the right approximations, which is not going to change the dynamics of the system. So the approximation that we make is, okay, delta I square. Delta I itself is a small quantity. Delta I square will be negligibly small. So I have neglected the delta I square term. And similarly, anywhere there are two delta, we are multiplying a small quantity with another small quantity, I have neglected that, right? So, and I think that this approach you guys would be pretty familiar with, right? So with that kind of an approach, this equation, whatever I had replaced, looks like this. You can actually do the equation yourself, but I'm not, I'm not showing the derivation. I mean, this is just replacement, right? There's nothing to, discuss as such. And now, once I have replaced, I have done the approximation. If at steady state, we know that this was the expression that was valid. So if I put in these equations here, what do I land up with? I land up with something like this. Again, you can do the maths, but you have to trust me that I am not cheated you guys. I am showing you the right equation. Okay, not a big deal. As I said, just so from here to here, I did the approximation, and on this equation, I just replaced the steady state or the equilibrium equation. I put it here, and then I come up with this, right? I do some rearrangement. So from here, I do some further rearrangement. Please note, yeah, this should be a black in color. This is a fixed number. I0 is fixed because we are talking of a constant current anemometer, right? And again, some more rearrangements. So if you now see what we are looking at, right? We have been able to, so what is the utility of, why did we do so much of math? So the maths, we did so much of maths because the goal is to come up with a transfer function of the sensor material. And what are the variables we have assumed here is delta I can be an input variable. That is what we are changing, right? Delta V, the velocity of the fluid, that also I'm treating it as an input variable because even though the fluid is not under our control, but it is fair to assume that the velocity will keep changing, right? So in a way, it is an input to the system. So delta V is also an input variable. Delta R is a variable, all right, but it is a dependent variable, right? So I have put the dependent variable on one side, and then same thing is MC by, I mean, this portion is how much the delta R itself is changing as a function of time. And this is with this constant, I mean, you know, I just, I mean, as I said, right, if you really look at it, this is nothing but rearranging and doing, I've just rearranged these terms. So not a big deal. You can look at it. You can probably at home when you have time, if you want to understand how this equation is being derived, please go through this. This is a mundane step which I'm not discussing, but the point is, the goal is I have taken delta I and delta V as two variables, two input variables, and with that, so I've rewritten that same equation again on this page just for continuity. Same equation is rewritten. With that, now I'm trying to make a mathematical model of the full system. So this guy, 2I0 delta I RW0. So this is one. So this is one portion, right? I'm representing this as Ki delta I, and this second portion I'm representing as Kv delta V, const, where Ki and Kv are proportionality constants. We are saying it's a constant because if you see here, so are we correct in saying that it is a constant? So that's where, so this is where you need to kind of think, is Ki really a constant or Kv really a constant or not? So yes, the point is around an operating point, even though UV0, this itself, UV is not constant, all right, but around a particular operating point, if we know the value of UV0, then we can say that yes, Ki is a constant. Similarly, Kv is another constant. And what do we see? That the resistor is going to change with a time constant tau v. And what is tau v? Tau v is, I've written this tau v because the tau is a function of the velocity of the fluid, right? So if I rearrange, if I take Laplace on both sides, I see that delta Rw, the resistance. See, we are good in dealing with resistances and capacitances, right? As electronics or electrical engineers, it is easy to measure the values of resistances or capacitances, right? So what we are doing is we are trying to come up with a transfer function, how the resistor is going to change with two input variables. One of them is, of course, the current, and the other is the velocity of the fluid, right? How does it look like? So now that we have come up with this expression, I am representing this mathematically in a block diagram form, and it's the same thing. You can see Kv. If I multiply this with the change in velocity or the change in current, this is nothing but, you know, just a mathematical operator addition, and multiply this with the time constant, we get delta Rw, the change in the resistor, right? So this is essentially what we have done is we have come up with a sensor wire model. And what do we see? So we are calling this a sensor wire, and is there any feedback in this? Obviously no, right? There is no feedback. So what we see is that yes, fluid velocity delta V can change. The current is under my control, and of course, if it is constant current anemometer, I can make sure that delta I is 0. So what happens is, so out of these two input variables, only one input is changing. I mean, only one signal we have, and based on that input signal, we will get a change in the resistor value. So if somehow we are able to measure the change in the resistor value, then we will get a measure of the velocity of the fluid. To this point, anywhere you think I have not been clear? Okay, so this is a system then without any feedback, and this is an open loop system, and we do see that there is a time constant associated with it, and the time constant is given by 1 plus s, the time constant is given by tau v, which depends on all these things. What does it depend on? It depends on, please note, the time constant depends on the mass. So what does that tell us? What do we want our time constant to be in a sensor? Do we want the time constant to be very high, or do we want it to be very low in these kind of applications? What do we want it to be? Common sense.
Very low.
Low, right? We want it to be low, as low as possible, right? So if we want tau v to be low, we see that the mass m needs to be as small as possible, right? And now does it make sense why we are using that thin wire? Why did we take so much of pain? One thing you guys can say that, look, we may want the resistor value to be high because we want it to heat up and all that, right? But the actual answer why that resistor, the wire needs to be thin, lies in this expression. Even the choice of the material, C, right? So if you were to do a sensor design yourself, once you understand this is the relation of the time constant, you can choose the value of m, c, and similarly, if you see here, the area, right? Area is coming, it is inversely proportional, right? So what do we want this area to be? We want the area to be as small as possible or as high as possible. Area to be as large as possible, right? We would want area to be as large as possible, right? But the problem is if we make the area very small and yet we want to have the mass area very large and yet we want to have the mass very small. So these are contradictory requirements. So that is where you will need to do a trade-off. How much? So that is where, so because we want the exposed area to be as large as possible, that's why we hold the wire 90 degrees to the fluid flow. So at least that we can do. Also someone can say, sir, why don't we use a thin film? Yes, we can use a thin film, but the problem is the moment, of course you can understand that, right? A film will have more mass than a wire. So then you are actually going to have a higher time constant associated with the film. We are going to look at that later on. When I show you a picture of the actual sensor in the modern world, I'm actually going to show you this, right? So these are the trade-offs, right? And then of course we see that it is dependent on I0 square and alpha RW, right? So what do we want? The choice of these guys also is going to impact your total tau v that you will end up getting. This is an open loop system, and this is only so much we can do. And these kind of time constants will be in the order of millisecond. I'm going to discuss this in the next slide. So what we can do, so this can be our constant current anemometer. This kind of makes sense, right? Again, our good old friend op-amp is back here in action. And because of the virtual short, assuming that this is an ideal op-amp, this current that will flow is the reference voltage divided by a constant resistor, RC, right? This is not immersed in the fluid. So please, that's why I have mentioned this as RC. It's a constant resistor. It is not it's not a part of the sensor material itself. The sensor sits here, RW. And if we can come up with this kind of a configuration, what will we get? The output voltage will be proportional to RW. Of course, there is a minus sign and all that. We can deal with it, minus and all. No need to get sweat too much about the minus, because we can always manipulate this in electrical domain, right? So we do get an output voltage, the magnitude of which is proportional to the RW, the resistance, right? And again, we know RW itself is proportional to the velocity, right? If we go back, right, RW itself, so delta I doesn't come into picture. This is delta RW. This is proportional to the velocity. Of course, there is a time constant associated with it, but then we know that delta V0 is proportional to delta RW, and if I replace RW with the, so sorry, this is a voltage here. Sorry, I think I mentioned this as velocity. So this the output voltage as a function of velocity is this, right? I've just replaced whatever I've got in the previous block diagram. I've just replaced that transfer function delta RW as a function of the velocity. So this is small v. So this is my velocity. I've just replaced this, right? So that means I now get an electronic system, the output voltage of which is a function of the velocity of the input velocity of the fluid, and of course there is a time constant associated with it, right? And for metal wire resistors, it is fair to assume that the resistor will have a function of temperature. It will be like this, right? I mean, this I think no need to explain. This is a fair assumption to make, right? The resistance will increase as a function of temperature. And in equilibrium, we had I square RW, we had this expression already. If you remember, we already had this expression. So that means, because we had this expression I square RW, I'm just replacing. So this I have to replace. I'm bringing this guy here, and I come up with an output voltage expression which looks like this. So this is my V. So this is, please understand, there is a difference between this and this. What is the difference between these two equations, guys? Can someone tell me? We derived all this. So here we are talking of delta V0, the small voltage change as a function of small change in fluid. So this is very important to understand. If you are doing an analog electronics course, right, you will exactly see these kind of problems, wherein you have to identify that the transfer function that we are talking about is based on small signal quantities. So these are small signal quantities, whereas this equation that we are dealing with is not just small signal, but it is an equation which relates the absolute, whatever is the value of the output voltage, it relates the output voltage to the absolute value of the fluid velocity. Make sense? Am I able to drive home the fact that these two equations, even though here also we are talking of V0, the output voltage, and here also we are talking of velocity. In this equation also we have V0 and we have velocity. But the difference between these two equations, the first one is dealing with small signal quantities, whereas this is dealing with absolute values. This is very important to understand. I cannot overemphasize the fact how important it is to differentiate between small signal and the absolute or the large signal equivalent relation. Any questions up to this point? Okay, so now that we have established this kind of instrumentation system, the realistic values of tau v is in millisecond, which may not be the most ideal thing for us, right? What do we want from a sensor? Whatever parameter we are sensing, we want the output to give us a measure of the input parameter or the input variable as quickly as possible, right? If there is a change in the velocity, you won't like to your instrumentation system to wait forever to give you a right measure of the change, right? So that's not a good thing. So the importance of tau v or the importance of time constant, that we already understand. There is a second problem with this kind of an arrangement. The second problem is the fact that we are keeping the current constant, we are letting the temperature of the resistance change. That creates a temperature cycling of the element. So basically, so these resistors right here, what we are showing is the resistor is a function of temperature. this is like, I would not call it a linear kind of variance. I mean, linear kind of equation between RW and TW. It is not. I mean, it is a straight line, all right, but it is in real electronic terms or in real technical terms, it is not a linear kind of relation. But then, in reality, the relation can be more involved. We do not want. So, for example, RW. So let's say this is our temperature, and the resistance probably will be looking somewhere. The resistance cannot be negative, and so this is R. So the resistance will probably look, let's say, something like this, right? It is not zero. This is not zero. So it is kind of looking like this, right? But in reality, if the temperature keeps changing, right, probably there will be a hysteresis loop, right? There will be some sort of a so this simple behavior of a straight line kind of equation may not hold good if we are subjecting the sensor element to temperature cycles. So that is the second problem. So we not only need to think of first order problems of time constant, but also we need to keep in mind that all these equations that we have derived is with certain assumptions. And the assumption in this case itself was that the resistor is a straight line, it has a straight line kind of a behavior as a function of the temperature, which may not be the case. If we are kind of stressing the sensor element again and again by varying different, I mean, if the temperature, we let the temperature kind of drift to, large, if we let the temperature swing for this resistor to a large quantity, that is not a good thing for the sensor element. Okay. Okay. So sorry. Yeah, so I think this animation was wrong. Anyway, this should have appeared here, but I did cover that this negative sign is not important. So I did mention this, so maybe I have to change the sequence of this animation. Okay, so now let us start looking at, so any questions up to this point? Have we successfully understood the concept of an operating point? So what all things did we learn in the last few slides? Of course, we talked about operating point and the importance of it, right? Also, we looked at how the transfer function, whenever we are talking of transfer function of a system, we are talking in small signal domain, not large signal, right? So distinguishing between a small signal domain and the absolute equations, that is the second thing that we learned, right? Third thing, of course, we learned to derive from a given sensor system, we learn to derive how we can represent the system in block diagram, right? Because once we are able to do mathematics, right? The beauty of mathematics is it gives us insight, right? Just like we discussed how the tau v, right? The time constant is dependent on the mass of the material, and that is the reason why the material needs to be a thin wire, or why it needs to be held in 90 degrees to the fluid velocity, right? So maths helps us giving insight to how the actual physical dimensions or actual controllable parameters, how we should be varying them, right? So it's important to actually look at the maths. So we learned to derive a transfer function, right? So derive a transfer function. And in that context, we again understood that again it's an open loop system. So the time constant is in milliseconds. So with that understanding, we will now go into the second kind of sensors that are actually most widely used now. So the constant current anemometer, I'm not sure. I did try to look in Google whether they actually use this at all anymore. I couldn't find any, but then I think this is very important. Even if that sensor is not used, this kind of constant current sensor, I couldn't find with whatever little time I spent, actual deployment of a constant current. Maybe there are some applications for sure, but then that does not make the discussion less interesting, because this is what is going to lead us to the concept of, or to a sensor structure, which will actually have a feedback, and we will see all these problems of tau v and temperature cycling, these will be gone. So it does not make the discussion any less relevant, even though we may not be using those kind of anemometers anymore. As I said, I looked at it, I may be wrong, but I couldn't find as such any modern day applications where constant current is actually used over constant temperature. But of course, CTA has been used, and this is the state of the art. So now let's look at a constant temperature anemometer and how the structure looks like. So now the fact that all the equations that we saw, right, those equations are still valid because we still have a sensor wire, a thin wire, being held with a much thicker wire probe, so that this resistance is negligible compared to this resistance, because our goal is to measure the change or the resistance in this guy, not in these arms, right? So so what we have done in this, please understand, and this again, I think Bentley has not done a good job of explaining the system. I mean, I totally disagree with what Bentley shows. In fact, I go on to make a point that it's almost bluffing the subject matter. It is incorrect. Whatever they have derived, the book says. I totally disagree with this. So please understand, please bear with me how I will approach this kind of a problem. So we have this wire sitting here, and so this is the tip. I've just shown a zoomed in version, which is of course we saw already in our previous coil. And this wire is a part of a whetstone bridge measurement. And then we have actually a transconductance amplifier and we have a voltage amplifier, both of which we can design. And being electronics engineers, we should be able to design these amplifiers. And then if we use this in a whetstone bridge, let's see what happens. And we will again derive the block diagram and see, And okay, by the way, so can you tell me whether this kind of a system, do you see any sort of a feedback? Can you identify the feedback? Because this is what we are discussing, right? In this phase of the lecture, we are focused on understanding why feedbacks are essential, right? So in this circuit diagram, can you identify the fact that there is a feedback? Can you tell? There is a feedback, right? Yes or no, guys? Give me an answer.
Yes, sir, like the current feedback.
Right. So there is a feedback loop, and the loop looks like this, right? There is a current feedback. And why do we need the current feedback? Because we want this material, this sensor wire, to have a constant temperature. So as we have discussed, that look, the resistance itself is a function of temperature, right? And temperature again is a function of the current. So if we want to make the temperature constant, what do we want to do? We need to change the current that is flowing in the whetstone bridge, right? So what we will do is, so please note these resistors are K times R, some constant, some algebra I've taken, K times R. And what we are ensuring is these resistor values, K times R, is much greater than, let's say, RC, right? And of course, in steady state, what will happen? These two voltages will be equal, right? Because this is an amplifier with a large gain or whatever. This loop has a large gain. We'll look at the transfer function and we will qualify why the loop has a large gain. And if the loop has a large gain, and if these resistors are equal, and this is much larger, we can approximate and say that most of the current that is flowing out of this transconductance amplifier, that current flows here. I mean, it's safe to assume that the current flowing in this KR is very little. KR is much higher, let's say 1,000 times higher, right? We can make that. And RC again is a constant resistor, right? So with that, this feedback, what is it going to ensure? it is going to ensure that if these two voltages are equal, what is it going to ensure? Can somebody tell me if this resistor is RW, what is the relation of RW and RC in this configuration? What will be the relation of RW and RC in this configuration because of the feedback? Come on guys, should be simple. Anyone? Ayush, Shubham, Ajay, Saurabh, Ashish, anyone?
Sir, equal.
Equal, correct. It will be equal, right? Because these two voltages are equal, right? Because of the feedback, these two voltages are equal. And what that means is, if let's say this voltage here is, let's say whatever, some VB, let's say the voltage of the bridge. So if this is VB by 2, so this point also will be VB by 2. So RC will be equal to RW, right? So what are we doing now is we are ensuring by feedback, we are ensuring RW also remains constant and equal to RC, which means, of course, that the temperature of the resistor is not varying. So this scheme, this feedback scheme of ensuring that the temperature is not varying, is this understood? We'll worry about this voltage later, but the feedback scheme is understood or not?
Sir, I could not understand how RC is equals to R.
You couldn't understand. So good. Good meaning. I appreciate the fact that you want to understand. And so, okay, it's like this. There is a feedback here. So just forget GM. GM is, I'm writing this as GM to denote that I'm changing the current here, right? For now, let's assume GM is very high, right? You can treat this as A also, because I think you will be more comfortable in dealing with A and assuming A to be very high, right? If A is very high, there is a feedback here, right? There is a feedback. There is a feedback in this mechanism, right? That you can identify, right? The fact that we are changing the current based on the voltage that we are sensing, there is a feedback, and the current is flowing in these arms, right? So what we are ensuring is, because there is an amplifier, a high gain amplifier, we are ensuring that these two voltages are same. Yes or no? That everyone will agree, right? That we can treat this as virtual short, right? If this is virtual short, let's assume the voltage at this point is VB. The bridge voltage is VB. And we have two resistors which are equal. These are large value resistors. So what will be this voltage? VB by 2, right? And because we have a feedback, yes, Saurabh, you want to say something?
No, sir. No, sir.
Okay, so because this is VB by 2 and there is a virtual short because of the amplifier, this node also will be VB by 2, yes or no? It will be VB by 2, right?
Yes, got it.
If this is also VB by 2, that means what? See, this is a wire and this is VB, right? The potential here is VB. So if this is VB by 2, that means the resistor, which is this guy, the sensor resistor RW, if this is VB, this is VB by 2, what does it mean? Means RW is equal to RC, right?
Yes, yes.
Okay. And this we are ensuring. Why do we need this? Please understand, we are actually incorporating the feedback. Why is feedback needed? Because we have to change the current flowing in this resistor to ensure that the temperature remains constant. And that is the reason we are calling it a constant temperature anemometer, right? We want the temperature to be constant. And if the temperature is constant, we looked at the resistor expression, right? RW is RW0, 1 plus whatever alpha T something, right? So only if the temperature is held constant will RW remain constant, right? So how are we ensuring that the temperature remains constant? By having this feedback mechanism. Okay. We'll stop here. Run out of time. Tomorrow we will derive the transfer function of this and then proceed and see what happens because of the feedback, what happens to the time constant and all that. And we will also look at what this guy is doing. I don't think this arrangement is shown in Bentley, but you can look at it. I kind of lost interest in Bentley on this section because, as I said, he has done some khapla on this. I completely disagree with what he has done. So anyway, we'll discuss this tomorrow.
Excuse me, sir. Hello.
Yes. Ayush.
But in the right part of circuit, if we think that if the op amp is virtually sorted, then we see that RC is sorted.
No, RC is not sorted. Please look at this. RC is not sorted, right? This is VB.
No,
RC
sir,
is not
on the
sorted.
left part. If like we see that gain 1 amplifier, and if
So forget that. So see this gain. No, there is no feedback with this. This is an open loop amplifier. This is an open loop.
Oh, okay. Sorry.
From here, right?
Yes, sir.
Got it right?
Yes, sir. Yes.
Yeah. Okay, we'll discuss this again tomorrow. And I don't think this is there in Bentley at all. So yeah, you have to bear with me to understand what I'm doing. Okay, we'll discuss tomorrow. Have a good day, guys. Bye.